Okay, welcome to section 8 in chapter 10. We're solving exponential equations. By some standard, this has been our goal all along. We're going to solve them two different ways. The simplest ones we can solve simply by translating, just like we did logarithms in our first look at those equations. We're also going to make logarithms a part of our algebraic operations, our algebraic toolkit. We're going to take the log of both sides. And we're going to do that because the log is the inverse operation of an exponential. So if you're solving a multiplication equation, you'd do division. If you're solving an exponential equation, you'd take logs. So let's start by solving equations by translating. This first equation has a base of 9 and an exponent of x. So we're going to translate that into log base 9 of 29 is x. And you can remind yourself that the base is 9 and the log is the exponent. So we see the log base 9 of 29 is x. And then to solve this, we get out our calculators, we use change of base, and rounded I get 1.5325. This next equation we cannot solve by translating yet. We have a coefficient of 3 there. So this isn't an exponential, this is a product. So we have to get rid of that 3. Multiplication is undone with division, so we're going to divide both sides by 3. Now we can translate it, and we're going to do that in the way you'd expect. The base is 6, the exponent is x. So if the base is 6, we're going to translate this as log base 6, and we remind ourselves that a log is an exponent. So there's our exponent of x. Again, we're going to get out change of base and put it into our calculator and get that x is approximately 1.6131. The next example, very similar. It's got that coefficient of 90. So we're going to have to get rid of it. That coefficient is attached by multiplication, undone with division. We're going to divide both sides by 90. So when we do that, we see that 6,795 divided by 90 gives us 75.5. We're going to translate this. The base is 1.25. The exponent is x. So x equals that log base 1.25 of 75.5. Again, change of base in our calculator. X is approximately 19.3783. The next example, we can translate it as we see it because we have a base and an exponent. Granted, the exponent is the opposite of x, but we can translate this as we see it. This is a log base 5 of 0.25, and that equals the opposite of x. We're going to get the x by itself, change the sign on both sides, and then put this into our calculator. Approximately 0.8614. The next two examples involve e, so let's take a look at that. We're going to translate these. They're going to be log base e's, which are going to become natural logs. The base is e, the exponent is 0.02x in this first example, so away we go. The log base e of 192 is that exponent 0.02x. Now, nobody writes the log base e. The log base e is, by definition, the natural log. So in the next step, we're going to rewrite that as the natural log. Now, we need to get the x by itself, and the x is attached to the 0.02 by multiplication, so undone with division. We put this in our calculator, and out comes approximately 262.8748. The next example has a coefficient. There's a 7 there, so we've got to get rid of it. It's attached by multiplication, undone with division. We're going to divide both sides by 7. Now we can translate it. The base is e, the exponent is negative 0.03x. So knowing that, we've got a log base e of 4/7 equals that exponent negative 0.03x. Of course, just like in the previous example, the log base e is the natural log, and we're going to need to do some division to get the x by itself. Into the calculator it goes. Notice you're only pressing the natural log key once here. You're going to divide inside of that logarithm. And out pops 18.6539 from our calculator. Now, taking logs is when logarithms become a part of how we see algebra. And taking logs means that we are going to take the log of both sides of an equation. And if we do, it still equals. So it's a property of equality. If A is equal to B, then we can take the log of both sides, any base we like, and we'll still have an equality. Now, we do this because logs undo exponentials. Remind yourself of the inverse operation section of Chapter 10. Let's first solve this same question by translating. I want to show you that you'll get the same answer by taking logs. Of course, if we solve by translating, we see that the base is 2 and the exponent is x. So we translate this as log base 2 equals the exponent x, of course, of 5. So there's our exact answer. We use change of base to put it into our calculator, and we get an approximate answer. Now, taking logs means just that. Just like we can multiply both sides by the same quantity other than 0, divide both sides by the same quantity other than 0, add and subtract to our heart's content, take square roots, all sorts of good stuff, we can now take logs as well. So we're going to do that. We're going to take the log of both sides. Now you may say to yourself, why don't we take the log base 2? That would save a little work. We're not being clever with this. We're simply trying to make logs a part of the way that we do algebra. When you see an exponential expression, like 2 to the x, think to yourself that that is undone with a logarithm. So when we take the log of both sides, we're going to use the power rule. When we talked about those properties of logs, the power rule stood out because of its ability to make exponents, well, that's what makes an exponential, into coefficients, and coefficients are just attached with multiplication. So in the next step, you're going to see that x coming out front. Now that means that that x is attached to the log of 2 by multiplication. In other words, I can get the x by itself now simply by dividing. And that's the power of the power rule. So if I want to get the x by itself, I need to divide both sides by the log of 2, and I get the same answer I got before. So taking logs, this is where Math 120 has given us a new way to do algebra. Now, of course, the only reason we would need this new power is when we're talking about exponential equations. So remind yourself of how powerful exponential equations are. Anything that grows at a constant rate is exponential. If a virus is spreading at a constant rate, its growth is exponential. We'd solve an equation involving that rate at which it's growing and how long it'll take to reach a certain number by using logarithms. Here's an example using our formula for compound interest. So we're going to solve this equation. It's got a 300 as a coefficient. You can probably pick out the parts of this. P is 300, R is 0.03, N is 4, and the accumulated amount, the ending amount A, is 500. Notice that the variable here is t, and it's in an exponent, meaning that this is an exponential equation. We've got a variable in the exponent. So at some point, we're going to take logs, but we can't yet, because when I look at that left side, the last thing that I would do to it, according to the order of operations, is not exponentiate. It's multiplying. So I need to get rid of that 300 before I do anything else. That's a simple enough matter. It's attached with multiplication, undone with division. So I'm going to divide both sides by 300. Now the left side is an exponential. The last thing I do is raise to that power. So I'm going to take the log of both sides, and that is exactly what we do. So we're taking the log of the left side and the log of the right side. Remember that that's making the left side and the right side into the argument of a function. We're not multiplying. Log is a function. Its argument is the old left side and the old right side. Now, what does this allow us to do? It allows the exponent to become a coefficient. So it was stuck up there in the exponent, and now it is attached with nothing stronger than multiplication. Now, of those two factors in the exponent, I'm really only interested in getting the t by itself. Notice that the 4 and the log are attached by multiplication. So no great surprise, the next step we're going to divide. We're going to divide by two things. So when you put this in your calculator, either use parentheses downstairs or divide twice. That tells your calculator that the 4 is downstairs and the log of 1 plus 0.03 over 4 is also downstairs. But however you put it in your calculator, parentheses or pressing the division sign twice, out will come a number of years. So I'm assuming this is years because it's t, and it looks so much like our formula for compound interest. So about 17 years. So here we're told to solve by taking logarithms. That's how I solve virtually all the exponential equations that I see. And we're told to use the equation for continuous growth. And there's a reminder of it. A equals P times E to the RT power. So we've got the equation. We're told to solve by taking logarithms. It says that the population of a small town is 15,000. That's its population now. That's P. It falls by 5% per year. We're going to do two things to that 5%. Because it's falling, it's negative, and because it's a percentage, we're going to convert it into a decimal, so 0.05. That'll be negative 0.05 when we take into consideration that the population's falling. It says how many years later? There's our variable t. That t in the exponent. Will the population be 10,000? That's our future amount. So we plug it into the equation, taking the place of what we've got. So 10,000, our future amount, taking the place of A. 15,000, our current amount, taking the place of P. And then, of course, our rate, negative 0.05. We have a coefficient. That right side is a product, so we need to get rid of that coefficient. It's attached with multiplication, undone with division. We divide both sides by 15,000. I divided out the thousands and I took the log of both sides. I took the natural log because it's a little easier to write, just two letters, and you can do it in cursive and it looks really nice. I'm now going to bring the exponent out front. I'm going to use the power rule, and that's exactly why we're taking logs. We're taking logs so that we can bring that exponent out front, make it into a coefficient attached with multiplication. Another thing I did is that I saw that I could divide out more than just thousands. On the left side, I noticed that I had multiples of 5. So there's 2 5s upstairs and 3 5s downstairs. So I simplified inside of the logarithm on the left side. Now, one other thing is about to happen, and hopefully you remember this from the identities. The natural log of e, well, that's the log base e of e. That's asking e to what power is e. I mean, that really is what it's asking. E to what power is e? And you say to yourself, well, an e is an e. That means the exponent must be 1. Well, anything times 1 is itself. So the natural log of e, we're not going to see it again. It's just giving us a factor of 1. So we've simplified a little bit, getting rid of the natural log of e. In a sense, it's still there. That's the 1 that means that nothing went away, nothing got any bigger. Now to get the t by itself, we're dividing both sides by negative 0.05. So now the t's on the left side, we've got the natural log of 2/3 over negative 0.05. When you put this in your calculator, and I'm sure I don't have to remind you of this, but it's always good to remember that there's a potential for making a mistake here. If you've got a calculator with 2 little dashes, one for subtraction and one for negative, make sure you use the negative on that 0.05. We put it on our calculator and out comes approximately 8.1093 years. I'm rounding everything to 4 decimal places. It says the population of Zimbabwe has been growing at 3%. It says if the population continues to grow at that 3%, how long until it doubles? So we're going to use that exponential formula. We're going to say that for every Zimbabwean there is today, for every one of them, we're interested in how long it will take for there to be 2. So for whatever the population of Zimbabwe is today, we're interested in figuring out when it doubles. So we don't need to show that 1, and we probably can write it without it. So there's 2 equals e to the 0.03. That's Zimbabwe's growth rate, t. And we take the natural log of both sides. So there's the 2, the argument of the natural log on the left, and the e to the 0.03t, the argument on the right. Now, on the right side, well, why are we taking logs? We're taking logs so that we've got the power rule. Out comes 0.03t, now attached with nothing stronger than multiplication. And on the right side, I've also got the natural log of e, which, just like in the previous example, gives us 1. So when we get the t by itself, we're going to divide both sides by 0.03. That gives us the natural log over 0.03. Now, at the very beginning of chapter 10, when we were just talking about why growth matters and how different growth affects the outcome so dramatically differently, I actually gave you the formula for doubling time, the natural log of 2 over the growth rate r. That constant growth rate r is 0.03 here. So if you remember that, you could go straight to the formula. You're free to use that. We'll derive it in a little bit. It's that powerful and useful to us. So the doubling time in Zimbabwe, when your population grows at 3% per year, every year will double in 23 years, which means that for most of you that are at least 23 years old, I'm assuming. That means that you've seen the population of your country double. For every 1 person there was when you were a kid, there's now 2. So something as small, or at least something that looks, or maybe at first glance seems as small as 3%, is actually pretty fast. That means that the population doubles in about 23 years. So it doubles again in another 23 years. That means 4 times as big. Doubles again in another 23 years. That means 8 times as big. There's really no way to sustain 3% growth. That's pretty extraordinary. Okay, a very similar question. Now we're asked to solve an equation, but we're asked to translate it using the compound growth formula. So the original amount is p, the growth rates r, the time in years is t, the number of compounding periods each year is n, and the later or the ending amount is a. So it says at the birth of a child, $10,000 is invested in a college savings account that earns 2% compounded monthly. That compounded monthly tells me that n is 12. There are 12 months in a year. And it says, how old will she be when the value of the account is $15,000? So 10,000 is our starting amount, P. The rate is 0.02. N is 12. And A, the accumulated or future amount, is 15,000. We plugged all that into the formula. We see that we have a coefficient on our exponential equation. In fact, the last thing that happens on the right side is multiplication. So it's not really exponential, it's actually a product. We divide both sides by 10,000 and take the natural log. Notice that I've got an ln on the left side and an ln on the right side. That's going to allow the exponent to become a coefficient. Also notice that 15,000 divided by 10,000 simplifies to 3/2. So we simplified inside the argument on the left side as well. On the right side, we've got the product of 3 things. A 12, which we want to get rid of. We'll divide by 12. The t, which we want to get by itself. And the natural log. So we're going to divide both sides by that 12 and the natural log. There we go. The parentheses, again, remember, when you put this into your calculator, you might want to put the denominator in parentheses. That's certainly one choice. Or you might want to press the division key on your calculator twice. 2 ways of getting out the correct answer, which is about 20.2901 years. So half again as much, earning 2% interest compounded monthly. The next question is about inflation. So if all this interest has bothered you or is something you're not comfortable with, any interest question can be rephrased in the context of inflation. So here's an inflation question. Inflation is just the loss of purchasing power of a particular unit of currency. So inflation causes a retirement savings account to lose purchasing power at 2% per year. How many years will it take the purchasing power to fall from $350,000 to $300,000? So here, the ending amount is actually less than the starting amount. That is the purchasing power. It fell from $350,000 to $300,000. So our future amount A is $300,000. Our present amount P is $350,000. It's falling at 2% per year, so notice we've got a negative there. And we're assuming that it's compounding annually, so N is 1. This simplifies really nicely. The division on the left side, when we divide through by the 350,000, gives us the natural log of that quotient. We're going to simplify that as we work through this problem. And on the right, 1 minus 0.02, we can do that arithmetic as well. So the first thing that I did is divided out 10 thousandths on the left, and then on the right, I actually did the subtraction. The natural log allows the exponent to become a coefficient, and of course we care about that because that exponent is our variable. That's the thing that we want to get by itself. So we want to know what that t is. Right now it's attached to the natural log of 0.98 with multiplication. We're going to undo that multiplication with division. So there is our exact value, the natural log of 6/7 over the natural log of 0.98. 6/7 because I divided out 5s from the 30 and the 35. We put this in our calculator, and out comes an approximation, and there's a scary thought, even relatively low 2%. This retirement account lost $50,000 in purchasing power in about 7.5 years, 7.6302 years. We've been focused on applications from the sciences, from math, from growth, anything that's growing and decaying. There's unique math problems here too, and this is definitely one of them. The first thing that you will notice about this problem is that the bases are different. 5 and 7, well, we cannot solve this equation by equating exponents because the bases are different. So this will give us an interesting challenge, an interesting way of reminding us about our algebra. There was a question like this in terms of how we solved this problem at the beginning of the semester when we were solving for a specified variable that appeared twice. So no great surprise. We want to get at those exponents. Of course we do. That's where the variables live. So we're going to take the log of both sides. That'll give us the power rule. The power rule will mean that the exponent becomes a coefficient attached with multiplication. So let's get started. We're going to take the log of both sides. I'm taking the natural log just because it's a little less writing, and I'm going to be writing natural log a lot. The exponents come out front. There they are. Notice you've got to have parentheses around the x plus 2 because it is a quantity being multiplied by the natural log of 5. That is all of it, not just parts of it. So on the left side, you're going to see distribution. On the right side, I might write the coefficient in front of the variable instead of after it. So not a big deal, but take a look at the right side. On the right side before, we had x times the natural log of 7. But I want to think of that natural log of 7 as a coefficient. I want to think of it like 3x. So I put it out front, and that focuses my mind on the natural log of 7 just being some number of x's. Now on the left side, we distributed. So the natural log of 5 got multiplied by x, and the natural log of 5 got multiplied by 2. Notice that there's x's on two sides of this equation. And we're not going to be able to do this arithmetic exactly because we're talking about the natural log of 5 as a coefficient and the natural log of 7 as a coefficient. So we're going to have to factor that x out. That'll be the only way that we can make 2 of something into 1 of something. I mean, division's another way, but it will give us stuff in the denominator. So we're going to go for factoring, and to do that, we're going to get the variable terms together. So it looks like we subtracted the natural log of 7x from both sides so that the x's are on the left, and we subtracted 2 natural log of 5s from both sides so that the constant terms are on the right. Now, on the left side, both of those terms have an x in it. So no great surprise, in the next step, we're going to factor those x's out. So here is the x that we factored out of both of those. And now we are so close to being done, and with it, the end of this section, that it's kind of nice to take a look at where we are. There's just one x now. That's the first time that's been true in this problem. That happened because of factoring. Now those parentheses tell me that the x is being multiplied by that difference of logarithms. So I can get the x by itself simply by dividing. So I'm going to divide both sides by the natural log of 5 minus the natural log of 7. Another reminder, I've said it each time, but if you put this in your calculator without parentheses, it's not going to know that the natural log of 7 is downstairs. So parentheses are really important when you're putting this into your calculator. And out pops the approximate answer, 9.5665.